year of Webb observations, scientists published over 600 papers based on its discoveries. So for at least 20 years, scientists around the world will keep peeling back the mysteries of the universe.
Something unbelievable has just been detected in the depths of space, and scientists are shaken to their core. Could everything we thought we knew about the universe be completely wrong? The James Webb Space Telescope has captured a mind-bending anomaly, one so baffling that even a Nobel Prize-winning scientist has issued a chilling warning. What did JWST uncover? And why is the scientific community in a state of disbelief? The truth might be more unsettling than we ever imagined. The ancient galaxy that changes everything. What was once just a faint blur in the vastness of space has now been revealed as one of the oldest galaxies ever discovered. Thanks to the powerful James Webb Space Telescope, scientists have uncovered the secrets of GZ9P3, a galaxy that existed just 510 million years after the Big Bang. For years, astronomers could only see a tiny speck of light, barely enough to study. But Webb changed everything. Not only did it confirm the galaxy's existence, but it also revealed something shocking. GZ9P3 was far more advanced than expected for its age. According to the GLASS project, Grism Lens Amplified Survey from Space, which focuses on detecting ancient galaxies, GZ9P3 wasn't just any young galaxy. It was likely the result of multiple smaller galaxies merging together, a discovery that completely challenges what we thought we knew about how galaxies evolve. In theory, galaxies could have started forming this early in the universe, but they were expected to be small and underdeveloped. Yet, GZ9P3 was already well formed, suggesting that galactic mergers happened much sooner than scientists previously believed. Even more fascinating, new data hints that GZ9P3 might still have been in the middle of merging when we captured its light, meaning it could have been actively growing and evolving at the time. The mystery of GZ9P3. GZ9P3 is a distant galaxy with a complex and chaotic structure. Its two bright patches reveal dense nuclei, suggesting it was born from the violent collision of two early galaxies in the young universe. Remarkably, this collision might still have been ongoing when JWST captured its image. The morphology of GZ9P3 strongly suggests an incomplete galactic merger, explained researcher Boyette. We can still see two distinct components, indicating the merger is unfinished. When massive galaxies collide, they eject some matter, and what we observed could be one of the farthest galactic mergers ever detected. But JWST's observations didn't stop at just structure and shape. The telescope provided unprecedented insights into GZ9P3's stellar population. Younger stars shine brighter than older ones, often dominating the visual profile of distant galaxies. Thanks to JWST's advanced spectroscopic analysis, researchers identified both a young, brilliant population, just a few million years old, and an older one, already surpassing 100 million years in age. Historically, galaxies that existed 400 to 500 million years after the Big Bang were considered rare and peculiar. Before JWST, Hubble's images lacked the clarity needed to confirm if these ancient objects were true galaxies or simply clusters of population 3 stars, the first generation of massive, short-lived stars. These stellar giants shone intensely, but burned out within millions of years, making their presence difficult to study. However, JWST has rewritten this cosmic story. Webb's detailed data now confirms that these bright patches of light hold millions, or even billions of stars, dismantling the earlier theory that early galaxies were just loose collections of giant stars. Moreover, many of the galaxies examined by JWST exhibit intricate structures like spiral arms and bars, proving they were already complex systems much earlier in the universe's history than previously thought. Yet, GZ9P3 stands apart as a true cosmic anomaly. Not only is it far more massive than expected, but it's also roughly 10 times larger than other galaxies JWST has observed from similar epochs. Its dual nuclei and chaotic form paint a vivid picture of an intense galactic collision, offering astronomers a rare window into the universe's turbulent early years. This discovery challenges our understanding of early galaxy formation and raises new questions about how such massive structures emerged so soon after the Big Bang. As JWST continues to peer deeper into the cosmos, GZ9P3 may be just the beginning of a new era of astronomical revelations. The Hubble Space Telescope. The launch of the Hubble Space Telescope in 1990 changed how we see the universe. Positioned above Earth's atmosphere, Hubble captures incredibly sharp images and detailed data, allowing us to explore everything from our solar system to the distant edges of the cosmos. Scientists from around the world compete for the chance to use this powerful tool through an open and anonymous review process. Hubble remains the only space-based telescope providing high-resolution ultraviolet, visible, and near-infrared imaging. Even with the launch of the James Webb Space Telescope, JWST, in 2021, both observatories continue to work together, pushing the boundaries of astronomical research and answering some of the biggest scientific questions of our time. One of Hubble's major contributions was refining the Hubble constant, which measures the rate of cosmic expansion. It also mapped star-forming regions in stunning detail using optical and ultraviolet instruments. However, those wavelengths could only reveal part of the cosmic story. As light from distant objects stretches over time, a process called redshift, infrared observations became essential to studying the early universe. This is where JWST comes in. With its massive 6.5-meter segmented mirror and cutting-edge infrared sensors, JWST can detect light from galaxies formed just a few hundred million years after the Big Bang. Unlike Hubble, JWST orbits at the second Lagrange point, L2, where its instruments remain shielded from the sun's heat, keeping them cold enough to capture faint infrared signals. When JWST reached L2, space enthusiasts worldwide held their breath as the telescope underwent a delicate unfolding process. The alignment of its mirror segments was crucial for producing clear images. When the first pictures arrived, they exceeded all expectations. One of JWST's most breathtaking early images was the Deep Field Snapshot, taken with its near-infrared camera, NIRCam. This image revealed thousands of distant galaxies, some so far away that their light had been stretched and distorted by gravitational lensing. Every tiny arc and swirl in the picture offers clues about the universe's earliest days, helping scientists piece together the story of cosmic evolution. Challenging the cosmos. The James Webb Space Telescope, JWST, continues to unlock the mysteries of the universe, pushing the boundaries of our understanding. One of its latest advancements involves fine-tuning its alignment with the near-infrared camera, NIRCam. As scientists gather data to refine the telescope's optical components, they are also testing other powerful instruments on board. One such instrument, the Near-Infrared Spectrograph, NIR-SPEC, is a game-changer. It features a micro-shutter array with 250,000 tiny, movable windows, each just 0.1 by 0.2 millimeters in size. This innovation allows scientists to target specific galaxies while blocking out unwanted background noise selectively. By doing so, JWST can analyze the chemical makeup, star formation rates, and velocities of celestial bodies with unprecedented clarity. But why does this matter? JWST has the ability to zoom in on galaxies that previous telescopes, like Hubble, identified as unusual. For example, if Hubble spots a galaxy that appears strangely bright and red, JWST can take a closer look, analyze its spectral lines, and determine its distance and star formation activity. Some of the most intriguing discoveries include galaxies like Jade's GSZ 14-1, which is believed to have formed just 290 million years after the Big Bang. That's incredibly early in cosmic history, raising big questions about how such a massive system could exist so soon after the universe began. Another shocking revelation is the discovery of galaxies that seem to have converted nearly all of their available gas into stars. Normally, only a small fraction of gas turns into stars due to limiting factors like supernova feedback and the availability of cold gas. But JWST keeps finding these so-called overachieving galaxies, suggesting that the standard models of star formation may need a major revision. These findings challenge long-standing theories about how matter behaves under gravity in the early universe. If JWST continues to reveal such anomalies, scientists may have to rethink the timeline of the Big Bang itself. One thing is clear: our understanding of the cosmos is evolving faster than ever, thanks to this revolutionary telescope. The Big Bang, a universe in question? The Big Bang theory is the widely accepted explanation for how our universe began. It proposes that everything started from an unimaginably tiny, hot, and dense point, which then expanded rapidly. Over 13.7 billion years, this expansion has continued, shaping the vast cosmos we see today. But what if some of our fundamental assumptions are being challenged? In the earliest moments, energy levels were incredibly high. The fundamental forces behaved differently, and subatomic particles formed and dissolved in ways that defy our imagination. About 380,000 years after the Big Bang, the universe cooled enough for neutral atoms to form, allowing light to travel freely. This event left behind a cosmic fingerprint known as the cosmic microwave background, CMB. Over millions of years, matter gathered into the first stars and galaxies, shaping the universe as we know it. However, recent discoveries by the James Webb Space Telescope, JWST, have thrown a curveball at our understanding. If the universe is around 13.8 billion years old, we would expect to see the first large galaxies forming roughly 500 million to a billion years after the Big Bang. Yet, JWST has identified well-structured, bright galaxies appearing less than 400 million years after the Big Bang. These galaxies are not small and chaotic, as expected, but instead contain many stars and appear mature. This contradiction has sparked debates among scientists. Some propose that the universe might be older than we thought. Others believe that galaxies formed more efficiently than our current models predict. Could extremely dense gas pockets or faster cooling rates have accelerated star formation? Another possibility is that some of these bright objects are actually ancient black holes, known as quasars, which might be distorting our measurements. Furthermore, our methods of calculating cosmic distances may need refinement. While redshift measurements are generally reliable, certain cosmic conditions could be misleading our interpretations. If these early galaxies are indeed as old and massive as they seem, it could force us to rethink fundamental aspects of the Big Bang model. The dark universe. Is space really empty? Not quite. The vast stretches between stars are filled with something invisible yet powerful: dark matter. This mysterious substance, along with dark energy, is central to the widely accepted lambda cold dark matter (LCDM) model, which explains the universe's expansion and structure. But what exactly are dark matter and dark energy? Imagine this. While dark energy pushes galaxies apart, accelerating the universe's expansion, dark matter works behind the scenes, holding galaxies together. Without it, the gravitational pull of visible matter wouldn't be enough to keep galaxies intact. Scientists estimate that the universe is made up of about 68% dark energy, 27% dark matter, and only 5% ordinary matter, the stuff we can actually see. The problem? We've never directly detected dark matter or dark energy in experiments. Yet, astronomical observations strongly suggest their existence. When the James Webb Space Telescope, JWST, spotted massive galaxies forming earlier than expected, it raised big questions. Did dark matter behave differently in the past? Was it clumping faster than we thought? Some scientists propose alternative forms of dark matter, like warm or self-interacting types, that might explain these surprises. Dark energy also remains a puzzle. Observations of Type Ia supernovae, stellar explosions used to measure cosmic distances, revealed that the universe's expansion isn't just continuing, it's accelerating. This discovery won a Nobel Prize, but new findings suggest dark energy's effects might have changed over time. Could an unknown force be at play? Some theories try to replace dark matter and dark energy altogether. Modified Newtonian dynamics, MOND, and other gravity-based ideas have been proposed, but they struggle to explain key observations, like the cosmic microwave background's patterns. Another mystery is early star formation. Galaxies aren't supposed to turn all their gas into stars too quickly. Stellar winds and explosions should slow the process. Yet, JWST is seeing galaxies that did just that. If early galaxies defied these expectations, what does that mean for our understanding of the cosmos? The universe is full of unanswered questions. Every new discovery challenges what we thought we knew, pushing scientists to rethink the very fabric of reality. Planetary secrets and cosmic mysteries. NASA's James Webb Space Telescope has captured stunning images of massive gas planets in a young planetary system. HR 8799, located 130 light-years away, has fascinated astronomers for years. Now, Webb's advanced imaging reveals new details about the system's planets, reshaping ideas about how these celestial giants formed. The findings confirm that HR 8799's planets contain high amounts of carbon dioxide. This strongly suggests they formed in a process similar to Jupiter and Saturn. Instead of forming instantly, they slowly built up solid cores before attracting surrounding gas from a protoplanetary disk. This process, called core accretion, has long been a leading theory, and Webb's data provides new proof. Beyond that, Webb has demonstrated its ability to analyze exoplanet atmospheres simply through imaging. This method is a game changer. Traditionally, scientists relied on spectroscopic instruments to determine atmospheric composition. But Webb's imaging capabilities opened up new possibilities. It means researchers can now study distant planets in more detail than ever before. But these discoveries do not stop at planetary formation. Webb has also uncovered an even bigger puzzle about the early universe. Astronomers have long believed that galaxies cannot efficiently convert all their gas into stars. This is because of several opposing forces: stellar winds, radiation pressure, and supernova explosions, pushing gas outward before it can form more stars. However, Webb is now detecting galaxies that appear to defy this rule. Some ancient galaxies seem to have turned nearly 100% of their available gas into stars. If true, this upends the standard models of galaxy evolution. What could explain this? One possibility is that gas in the early universe was much denser and cooler, allowing stars to form rapidly without interference. Another theory suggests that some of these early galaxies were unusually compact, which may have helped them retain their gas rather than lose it to external forces. Scientists also wonder if unique radiation environments or hidden cosmic processes altered how gas collapsed into stars. There is even a chance that some of these objects may not be galaxies at all. It is possible that highly active galactic nuclei, such as quasars, could be shining so brightly that they mimic the appearance of densely packed galaxies. This is why follow-up observations using Webb's spectroscopic tools are critical. These unexpected discoveries show just how much Webb is changing our understanding of the cosmos. As more data comes in, astronomers will continue to question long-standing theories and uncover new mysteries about how planets, stars, and galaxies evolve. The Hubble tension. The universe is expanding, but how fast? That's the puzzle at the heart of the Hubble tension, a major cosmic mystery that has baffled astronomers for years. Two different methods are used to measure this expansion, but they don't match up. One approach examines nearby celestial objects, such as supernovae, to calculate the Hubble constant. The other relies on data from the early universe, particularly the cosmic microwave background, to infer what the value should be. In theory, these methods should give the same answer, yet they don't. Instead, they produce conflicting results, leaving scientists searching for explanations. One possible answer? A phenomenon known as early dark energy. Unlike the dark energy that drives today's accelerated expansion, this force may have existed only briefly, just a few thousand years after the Big Bang. Acting like a temporary anti-gravity effect, it could have sped up the universe's early expansion, bridging the gap between the two measurements. Early dark energy is one possible addition to the standard cosmological model that would preserve its many successes and resolve the Hubble tension, said Michael Boylan-Colchin, an astronomer at the University of Texas at Austin. But is this truly the missing piece of the puzzle, or is there something even stranger at play? The numbers behind the Hubble tension make the problem impossible to ignore. Observations of supernovae suggest the universe is expanding at around 73 to 75 kilometers per second per megaparsec. But when astronomers study the cosmic microwave background, they get a lower rate, around 67 to 69. Both sets of measurements have grown increasingly precise over the years, yet the gap remains stubbornly unchanged. This is not a minor disagreement. It's a fundamental clash in our understanding of the cosmos. If both methods are correct, then something is missing from our current models. Could the answer lie in the earliest galaxies? Recent discoveries by the James Webb Space Telescope, JWST, have shocked astronomers, revealing galaxies that appear far more developed than expected. If galaxies formed faster than previously thought, it could shift our understanding of cosmic distances and expansion rates. This, in turn, might influence the Hubble tension. However, astronomers remain cautious. More data is needed to determine whether these findings truly challenge the standard model or if they can be explained within existing theories. New telescopes, including the upcoming Nancy Grace Roman Space Telescope and ESA's Euclid mission, aim to collect even more precise measurements. Their data could either confirm the Hubble tension as a real, unsolved problem or expose hidden errors in our current methods. If the discrepancy persists, it might force scientists to rethink fundamental aspects of cosmology, including our understanding of dark energy and inflation. The ancient echo of the Big Bang. The universe holds secrets beyond imagination, and among them, the cosmic microwave background, CMB, stands as a ghostly relic of the first light that ever traveled freely. This faint glow, a whisper from the Big Bang, lingers across the cosmos. It is the oldest light detectable, a fossilized snapshot of the universe's infancy. Scientists refer to it as an echo, a shockwave of creation itself. Its discovery happened by accident. In the year 1965, two radio astronomers, Arno Penzias and Robert Wilson, detected an unusual signal in their telescope. It was present everywhere and remained constant in strength regardless of the time of day or season. Suspecting interference, they checked their equipment thoroughly, even removing pigeons that had nested inside. Yet the signal persisted. Finally, they realized it was not coming from Earth, nor even from the Milky Way galaxy. It was a message from nearly 14 billion years ago. Long before galaxies and stars existed, the universe was a chaotic, scorching hot ocean of particles. Atoms could not form because charged particles scattered light endlessly. Then, after 380,000 years, temperatures dropped, allowing neutral atoms to appear. Light was set free, and as space expanded, that ancient radiation stretched into microwaves. Today, this glow arrives from every direction, carrying crucial clues about the universe's past. Mapping the CMB reveals more than just leftover heat. It holds the fingerprints of creation itself. Tiny temperature variations seen in data from the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite hint at the seeds of galaxies and cosmic voids. These patterns trace back to an era of rapid expansion called cosmic inflation. If this theory is correct, quantum ripples from that early burst evolved into the vast cosmic structures seen today. Yet, mysteries remain. Certain anomalies in the CMB puzzle scientists. One of the most baffling ones is the cold spot, a massive region of lower temperature that defies easy explanation. Some suggest it hints at exotic physics, possibly even a collision between our universe and another. Others argue that the standard model of cosmology may require revision. Challenges to the Big Bang and the expanding universe. Observations from telescopes like the James Webb Space Telescope, JWST, provide fresh tests of existing theories. If early galaxies appear different from CMB-based predictions, something might be wrong. Scientists compare these cosmic snapshots to see if the structures of the early universe match expectations. Any inconsistencies could suggest a missing piece in our understanding of the cosmos. Did the universe expand differently than thought? Could inflation be incomplete or even incorrect? Inflation itself was proposed to solve multiple problems. It explains why the universe looks so smooth on a large scale, why it lacks expected features like magnetic monopoles, and why its geometry appears nearly flat. But what if inflation never happened? Some scientists propose a bouncing universe, one that cycles through endless expansions and contractions. Others suggest an ever-existing cosmos with no true beginning. Quantum physics might hold the key. In its earliest moments, the universe was an extreme-energy laboratory where space and time blurred. High-energy experiments today, such as those conducted at the Large Hadron Collider, attempt to recreate these conditions. Deep underground, detectors search for dark matter, another missing piece of the cosmic puzzle. The link between particle physics and cosmic expansion remains one of the biggest unresolved questions in science. Some physicists believe string theory could provide answers. In this view, all particles are tiny vibrating strings moving through hidden dimensions. If correct, it could unify gravity and quantum mechanics. However, proving it is a challenge. The early universe may be the only place where such extreme energies ever existed. If anomalies in the CMB hint at extra dimensions or unknown physics, they might be the best clues available. Could the Big Bang itself be an illusion? Certain quantum gravity models suggest that space-time, as we understand it, breaks down at the highest energies. Instead of a singular explosion, the Big Bang might have been a transition between different cosmic states. If JWST finds galaxies older than expected, established timelines could collapse. Perhaps the universe's true history is far more complex than imagined. Beyond what we can see, the cosmos continues. The observable universe stretches across 92 billion light-years, yet beyond that, light has not yet reached us. In some regions, space expands faster than light, meaning vast portions of the universe remain forever hidden. Does space have an edge? If the universe is infinite, then the answer is no. If it is finite, what lies beyond? Some scientists propose the existence of a multiverse, where infinite universes form through endless cycles of inflation. If true, subtle imprints of cosmic collisions might be present in the CMB or galaxy distributions. However, detecting such evidence remains a major challenge. The universe guards its secrets well. Without concrete proof, these ideas remain speculation. The search for answers continues. New observations, advanced instruments, and deeper theories may one day unveil what happened in the first moments of time. The universe does not easily reveal its mysteries, but each unexpected anomaly and each strange observation bring scientists closer to understanding the cosmic story written in its oldest light. We hope you enjoyed this video. Stay tuned for more amazing stories.